Hello guys, welcome to another video, and in this video we are going to try to find out some of the properties of moment generating function and characteristic function and stuff like that for the Poisson distribution. And obviously we'd be trying to look forward to what we have learned in the previous sections, including the first moment, the second moment, the third moment, higher moments, which we also call the bell numbers. So in the last video we did a lot of things, but in this one we would try to focus a bit on the part of MGF, or what I call, this is the MGF. This is called the moment generating function. So we are going to study this. Okay, so the MGF, let me define it properly first for the discrete case, and then I can define it for the continuous case, and then we can get on to with it for different distributions and for different parts. Okay, so since this I'm covering MGF for Poisson distribution, I might as well cover it for general distributions as well. So this might be a long video, but we are going to learn it completely. So what is MGF? MGF is a function which gives us an infinite series of moments okay. So MGF is basically an infinite series of moments. So how do we define it? So for RVX, if its PMF is probability of x, then, so let's say this is the PMF, that is the PMF function, probability mass function, then the MGF is defined as mx t equals to summation, take a small y over the whole sample space. And what you can do is, we actually need to find out the expectation of e to the power tx. So what we do is we do this into probability of x y. So this is the MGF in real terms, where t is obviously a real number, a parameter. It's a parameter which we use to find, but we do not really need this parameter. So in general words, the moment generating function is just the expectation of e to the power tx. E to the power tx is basically the expectation of which we call the moment generating function, and this definition is true regardless of if it is a discrete random variable or it is a continuous random variable. Okay, so let us try to find some examples here so that we can understand what's going on in a much more better way. So firstly, let us do it for the Poisson distribution, because this is important. In the discrete case, the Poisson distribution is very important, and obviously the MGF of it is also important as well. And we shall see how to derive the moments from MGF in a much more similar way, and we would know that how the MGF actually helps us to find the PMF or PDF of joint distributions easily than we could have hoped, because it really is a very useful tool. So what is the Poisson distribution? We know that let x be Poisson of lambda, then the PMF is probability of x equals to k e to the power minus lambda to the power k divided by k factorial for k equals to 0, 1, 2, ... right? So this is the Poisson distribution. Now since this is a Poisson distribution and we are interested in finding the MGF, we can see that the MGF is, as I told you, the MGF is denoted by a capital M. We given subscript the random variable for which we are finding the MGF, and we denote a parameter t, and it is given by the expectation of e to the power tx, right? Now, by the law of unconscious statistician, that is the lotus rule, we can see that this is basically equal to k equals to 0 to infinity, that is summing over all the values of the random variable, e to the power tk into the probability, which is e to the power minus lambda, lambda to the power k divided by k factorial. So this basically is the definition, and we can simplify it further as follows: k equals to 0 to infinity e to the power tk, lambda to the power k, e to the power minus lambda divided by k factorial. Since e to the power minus lambda is a constant, we can bring it outside to find that this is essentially equal to lambda e to the power t whole to the power k divided by k factorial. And as we know the Taylor series for e to the power x is, since I have not mentioned it in this lecture, so I'm going to just write it down once again. E to the power x is basically for all x belongs to real. Then the above moment generating function would be mxt is e to the power minus lambda k equals to 0 to infinity lambda e to the power t whole to the power k by k factorial, and this thing becomes e to the power lambda e to the power t, and in all we get e to the power lambda into e to the power t minus 1, right? This is the moment generating function, right? Also what we see here is the moment generating function can be differentiated in order to find the moments. Why is that true? We shall prove it right now. So firstly, consider that mxt is equal to expectation of e to the power tx, right? Now expectation of e to the power tx in normal ways is basically equal to, let's say, k equals to 0 to infinity e to the power tk probability of x equals to k, right? Now if we were to differentiate this moment, this function which is a function of t, right? If we were to differentiate it one times, what would you get? You would get this equals to k equals to 0 to infinity k e to the power tk probability of x equals to k, right? And therefore if you put in the value 0, what you get is this. Which basically is the first moment, isn't it? So in general, since it's the exponential function, if you differentiate it n times, what you get is this. So differentiating n times and putting 0, what you would get is k equals to 0 to infinity k to the power n probability of x equals to k, which basically would be the nth moment, right? Now we find out that for the Poisson distribution case, now let us see if this actually works, because we would know if it works because as we have already found out the moments by hand in the previous sections using the method of infinite series. So let us see. For Poisson distribution, we have that So therefore, let us find the three derivatives first, and then we shall move on to find the moments. The first derivative here would be d dt of e to the power lambda e to the power t into e to the power minus lambda, right? So e to the power minus lambda is a common, so it can be taken out of the differentiation, and what we get is this. Now this differentiation would be, firstly we would write out e to the power lambda e to the power t multiplied by lambda e to the power t. This would give us lambda outside e to the power t minus lambda plus lambda e to the power t. This would be our entire expression here, right? So this is the first derivative. The second derivative would be just the derivative for the derivative of the first derivative, right? The derivative of the first derivative is lambda e to the power t minus lambda plus lambda e to the power t. Since lambda is a constant outside, it can be taken outside of the differentiation term, and this becomes lambda into d dt of e to the power t minus lambda plus lambda e to the power t, and this also becomes lambda into e to the power t minus lambda plus lambda e to the power t into 1, and since this e to the power t minus lambda, so the differentiation of t is 1, lambda is 0, and lambda e to the power t is differentiation would be lambda e to the power t. So this should be our required answer here for the second derivative. Now the third derivative, again we can just write it out in a clear way like this. Lambda squared e to the power 2t minus lambda plus lambda e to the power t. Now the third derivative would just be the derivative of the second derivative, right? And the third derivative can be found as, so this term we already did. This is basically the second derivative. This is basically the first derivative which we differentiated to find out. So the answer for that would just be this whole thing again. So we already have lambda e to the power t minus lambda plus lambda e to the power t plus lambda squared e to the power 2t minus lambda plus lambda e to the power t. This would be the answer only for the derivative of the first term, because this basically is mx derivative t. And for this term, the next term, we have lambda square into d dt of e to the power 2t minus lambda plus lambda e to the power t. So simplifying, what we get is mx triple dash t is equal to, let's write it below so that we have more space, lambda e to the power t minus lambda plus lambda e to the power t plus lambda squared e to the power 2t minus lambda plus lambda e to the power t plus lambda squared e to the power 2t minus lambda plus lambda e to the power t multiplied by 2 plus lambda e to the power t. So this gives you the third derivative as well. Now it's time to check if the moments match. So E of x should be equal to this, right? So what is this? Let's go back and check. This should be this thing, lambda into e to the power t minus lambda plus lambda e to the power t with t at 0. So this should be lambda e to the power 0 minus lambda plus lambda e to the power 0, which is lambda e to the power 0 minus lambda plus lambda, which is lambda e to the power 0, which is lambda. So this one is correct. The first moment is in fact correct. Now the second moment. Second moment is basically given by mx double dash 0, and this is this part. So we can write it as lambda e to the power 0 minus lambda plus lambda e to the power 0 plus lambda squared e to the power 0 minus lambda plus lambda e to the power 0. This gives you lambda e to the power 0 plus lambda squared e to the power 0, which gives you the answer as lambda plus lambda squared, which is also correct for the second moment. And for the third moment we have as we can see above, the answer is this. So we already know the first two parts give you lambda plus lambda squared, and let's do the last part, which is this one. This is lambda squared into e to the power how much, 2t minus lambda plus lambda e to the power t into 2 plus lambda e to the power t. So 2t minus lambda, so 0 minus lambda plus lambda e to the power 0 into 2 plus lambda e to the power 0. This gives you lambda plus lambda squared into 2 plus lambda, which gives you lambda plus lambda squared plus 2 lambda squared plus lambda cube. This gives you lambda cube plus 3 lambda square plus lambda. So the expectation of x cube is lambda cube plus 3 lambda square plus lambda, which is also correct as we have found in our previous explorations. And we can see that how the moment generating function is so much useful in order to find moments of different genres, right? So this completes it, and we shall explore about the moment generating function in detail with the characteristic functions in the next sections as well, where we are going to need a little bit of integration first in order to understand the continuous random variables that we are going to get into, and later we would be coming back to the geometric distribution and different kinds of discrete distributions, because those require like special attention. So we actually need some basic info on infinite series and integrals before we can jump into the higher sections and advanced sections, just as a footnote. And before that I would also be able to solve you some problems on continuous random variables after I introduce them. So in the next lecture we shall do a basic footnote for integration and summation of infinite series. So that would cover like 3 to 4 videos, but hopefully that would cover at least how much we need to understand at this point right now. Okay, so thank you for watching this video. I'll see you in the next video, and do not forget to check the description for the Brater Maths app. It's a maths app where you have all the lectures and notes regarding the video solutions also, which I'm giving here. The lecture notes for this and written theory is also available there. Please do check out. Thank you. Of x equals to k, e to the power minus lambda, lambda to the power k divided by k factorial for k equals to 0, 1, 2, ... right? So this is the Poisson distribution. Now since this is a Poisson distribution and we are interested in finding the MGF, we can see that the MGF is, as I told you, the MGF is denoted by a capital M. We give in subscript the random variable for which we are finding the MGF, and we denote a parameter t, and it is given by the expectation of e to the power tx, right? Now, by the law of unconscious statistician, that is the lotus rule, we can see that this is basically equal to k equals to 0 to infinity, that is summing over all the values of the random variable, e to the power tk into the probability, which is e to the power minus lambda, lambda to the power k divided by k factorial. So this basically is the definition, and we can simplify it further as follows: k equals to 0 to infinity, e to the power tk, lambda to the power k, e to the power minus lambda divided by k factorial. Since e to the power minus lambda is a constant, we can bring it outside to find that this is essentially equal to lambda e to the power t whole to the power k divided by k factorial. And as we know the Taylor series for e to the power x is, since I have not mentioned it in this lecture, so I'm going to just write it down once again. E to the power x is basically for all x belongs to real. Then the above moment generating function would be mxt is e to the power minus lambda, k equals to 0 to infinity, lambda e to the power t whole to the power k by k factorial, and this thing becomes e to the power lambda e to the power t, and in all we get e to the power lambda into e to the power t minus 1, right? This is the moment generating function, right? Also what we see here is the moment generating function can be differentiated in order to find the moments. Why is that true? We shall prove it right now. So firstly, consider that mxt is equal to expectation of e to the power tx, right? Now, expectation of e to the power tx in normal ways is basically equal to, let's say, k equals to 0 to infinity, e to the power tk, probability of x equals to k, right? Now, if we were to differentiate this moment, this function, which is a function of t, right? If we were to differentiate it one times, what would you get? You would get this equals to k equals to 0 to infinity, k e to the power tk, probability of x equals to k, right? And therefore, if you put in the value 0, what you get is this. Which basically is the first moment, isn't it? So in general, since it's the exponential function, if you differentiate it n times, what you get is this. So differentiating n times and putting 0, what you would get is k equals to 0 to infinity, k to the power n, probability of x equals to k, which basically would be the nth moment, right? Now we find out that for the Poisson distribution case, now let us see if this actually works, because we would know if it works, because as we have already found out the moments by hand in the previous sections using the method of infinite series. So let us see. For Poisson distribution, we have that so therefore let us find the three derivatives first, and then we shall move on to find the moments. The first derivative here would be d dt of e to the power lambda e to the power t into e to the power minus lambda, right? So e to the power minus lambda is a common, so it can be taken out of the differentiation, and what we get is this. Now integral of f of gx d of gx, or you can say this is equal to f of y dy, where y equals to gx. So you just need to integrate the function f. If the function f is integrable to you in an elementary form, you would be done, right? Okay. So what we are trying to find is, if we can find something, some function which is a function of something, and the derivative of that function is already given along with dx, we can directly substitute that function. Why? We can see why. So given integral is I equals to 2x into root over of 1 plus x square dx, and we can substitute y equals to 1 plus x square. Why are we doing that? Because see, I realize that the integral of 2x into root over 1 plus x square can be solved if we were to eliminate this root over 1 plus x square thing. So when I substituted y equals to 1 plus x square, I saw that the derivative of 1 plus x square is just 2x, which is given along with dx. So 2x dx would be substituted into a single dy, which is what we wanted, which is basically the form of this function, right? So the derivative of 1 plus x square is already given outside. So when we do dy, what we get is 2x dx, and that is helpful because this turns into root over y into dy, where 1 plus x square got to y and 2x dx was written as dy. And this is an easy one because this is just y to the power half dy, and using the rule you can find it as y to the power half plus 1 divided by half plus 1 plus c, which is basically y to the power 3 by 2 into 2 by 3 plus c, which is the answer, right? So this is the integral and this is the answer, and we can just substitute back to get our answer in terms of x, obviously. So it is basically 2 into 1 plus x square to the power 3 by 2 whole by 3 plus c. This is our integral, right? So this type of integrals can be solved, but you need to be a bit cautious about them. So let us do another one. Evaluate dx. So we want to evaluate 4x by root over of 2x square plus 1 dx. Again, it should be noted that ddx of 2x square plus 1 is equals to ddx of 2x square plus ddx of 1, right? And ddx of 2x square is just 2 into 2x, and ddx of 1 is 0, which gives you 4x. So you see that 4x is already present. The derivative of the term of 2x square plus 1 is already present. And if that is so, what we can do is we can substitute y equals to 2x square plus 1, and thus we see that dy is equals to 4x dx, and this would turn our integral into something like this. But this just only means that it's y to the power minus half dy, and using the rule we can write it as minus half plus 1 by minus half plus 1 plus c, which is basically y to the power half, and this becomes 2 because it's a half in the denominator. And we can substitute back our answer to find it's just 2 into root over 2x square plus 1 plus c. If you differentiate this using the chain rule, you would find that the answer is basically 4x in divided by root over 2x square plus 1, which is amazing because differentiating something is very easy while integrating something is insanely hard, just because of the methods or the ways you have to look for, right? Okay, let's do another one. Evaluate sine of root x by root x dx. Now again in this one, as you can see, the only portion that is not going with the integral is the root x inside the sine, right? And we are kind of sure that whatever else is present in the integral should be the derivative of that, right? So let's see. We observe d dx of root x is just equal to d dx of x to the power 1 by 2. Now we have learned previously that the d dx of x to the power something is just the coefficient comes out, so the coefficient comes out and the coefficient the power comes out as a coefficient and the power is reduced by 1, which means it is half into x to the power minus half, or in other words 1 by 2 root x, right? So if we were to differentiate, what we would get is something like this. Let y equals to root x, then dy should be equals to dx by 2 root x, right? But we see dx by root x is also present, so what we get from this equation is dx by root x should be equals to 2 dy, and we can absolutely put this to get the integral as for I equals to sine of y, because root x is y, into 2 dy. Since 2 is a constant and is in multiplication with the rest of the integral, it comes out and we only have to integrate sine y dy, which is just minus cos y, so it's minus 2 cos y plus c, and putting the value of y back, what we get is minus 2 cosine of root x plus c. This is the answer, right? So you see, like, this kind of integrals can be solved, but then again we have to be a bit cautious. So let us solve a lot more problems. Example 7. I will try to do this as much as I can so that you get the idea of method of substitution completely. And if you have any trouble in evaluating derivatives, please go back to the last videos to find out how to evaluate a certain derivative or how to do complex derivatives as well. Okay, so example 7, evaluate integral of 2x e to the power x square minus 5 dx. So let us denote the integral by I, so that I is equals to 2x into e to the power x square minus 5 dx. Note that now again in this integral we are trying to see that since the derivative of x square minus 5 is just 2x, what we can do is y equals to x square minus 5, which should give us dy is equals to 2x dx, right? Then on substituting, I is equal to e to the power y and the 2x dx becomes dy, right? And you know the integration of e to the power y is just e to the power y plus c, and you put in the value which was x square minus 5 plus c. So this type of integrals, if you find the derivative of a term directly present inside the integral, try to substitute for that term so that you can reduce it into a common integral or an integral that you know of, okay? Because only then would it be easier for you to find out what to do. So we will continue our examples, but first let us learn one more thing. Let us do one more example, then from the next one From the next video we shall also do all the other indefinite integrals that we are required to do in the method of substitution, but also we will do some of the definite integrals, and we will learn how to do the definite integrals as well. So let us do this. This would be example 8, right? Yeah. So we'll continue from example 9 in the next video. So this would be the last example for this video. So let us do this problem where we have integral of cosine of x dx by 1 plus sine x. So this one looks a bit more tedious than before, but note that ddx of sine x is just cos x, right? So as we can see, cos x dx is present in the numerator and 1 plus sine x is in the denominator. So if derivative of sine x is cos x, then derivative of 1 plus sine x should also be cos x, right? So rather than going for the substitution y equals to sine x, what we can do is we can directly go for the substitution 1 plus sine x, then let y equals to 1 plus sine x, and from that we get dy is equals to cosine of x dx. This would give us our integral as y equals to integral of dy divided by y, which is just the integral. This integral is evaluated as a natural logarithm, right? So ln of y plus c, and remember the y is always positive, so it's rather a modulus. So the answer by putting back the value of y would be ln of 1 plus sine x plus c, which is the answer. So these are by far right now the easier parts of the integral, but we shall do some more integrals to find out how to do them, and then we shall move on to the next part where we learn how to do methods integration by substitution, and some other methods for evaluating indefinite integrals, such as, let's say, the surds and the radicals. And finally we can move on to definite integrals, which are of utmost importance, which is why you are learning indefinite integrals, right? So let me introduce you to you the new concept, which is integration by parts rather, and then we can continue solving problems which are mixed from both the sections. So integral by part, which is also known as IBP in short. So as the name suggests, it is actually a rule to find out integrals of the form where you have two functions fx into gx dx. What we do here is we try to name or label the functions as function 1 or function 2, and once we do that, we can have an easier rule to find out the integral in terms of another integral, which might be easier to solve. So as of derivatives, it does not obviously give you a direct answer, but it rather gives you a newer integral which might be easier to solve, and we have a rule for it. The rule is something like this. The rule is called ILET. I for inverse functions, L for logarithmic functions, A for algebraic functions. Algebraic functions means function of polynomials like x cube, x to the power 4 plus 2, and something like that. Logarithmic is involving log, inverse is involving sine inverse x, cos inverse x, tan inverse x, like that. So the inverse trigonometric functions. T is for only trigonometric, and E is for exponential. So why is this order important? This order is to choose the function that you choose which is higher up the list, which is like if the function, there are two functions in multiplication form, which is one of them are inverse and another one is algebraic, then you would have the inverse function as the first function and the algebraic as the second function. So if the function is higher up on the list, you would name it as function 1 and the other one would be function 2. So let us name here fx as function 1 and gx as function 2. Then what it gives you is function 1 directly comes out into integral of function 2 dx minus integral of derivative of function 1 into integral of function 2 dx multiplied by derivative of function 1 and the integration of this whole. So this is how it works. So you take the first function and you multiply it by the integral of the second, and you subtract from it integral of derivative of the first function into integral of the second function. So let us take some examples so as to understand how this works. Example 1. Let us find out the derivative of x log x dx. Okay, so identify x is an algebraic function, right? ln x is logarithmic. So which one is more up the list? Obviously L, right? So L should be treated as the first function and x should be treated as second function. So denote the integral by I. Integral by I, and what we do get here is I equals to integral of x log x dx. Given that log x, we are denoting log x as first function, x as second function, which means we should have first function into integral of second function minus integral of derivative of first function, which is just 1 by x, into integral of second function and the integral of the whole thing, right? So integral of x dx is just x square by 2, right? So it should be x square ln x by 2 minus, we have already found the derivative for log of x, which is 1 by x, and again integral of x is x square by 2. So in this inner integral you do not need to include the constant plus c, so we are basically trying to just find the integral and accept the constant. So 1 by x into x square by 2 dx, and as we can see this becomes x square ln x by 2 minus integral of this x is cut off, it's x by 2 dx, which can also be evaluated because x square log of x by 2 minus this is x square by 2, so this is x square by 4. Now we can include a plus c to complete our answer. So x log x could not be evaluated otherwise. The only way is to guess the function whose derivative is x log x, which is kind of impossible. So we do not really need to follow that strategy, obviously, but this would give us the answer, right? Okay, so let us try to find out some more problems. For the next problem, what we do need is this: d dx of tan inverse x is equals to 1 by 1 plus x square. We are going to prove it, but first understand that since the derivative of tan inverse x is 1 by 1 plus x square, this also means that integration of 1 by 1 plus x square is equals to tan inverse x plus c. Okay, and how do we prove it? Okay, so let y equals to tan inverse of x, then what we see is x should be equal to tan of y, right? And what we are trying to find is dy by dx, so let us see how to find that. And the derivative of tan y is sec square y, if you remember it from the derivative section. So differentiating both sides, we get dx equals to sec square y dy, and sec square y is just 1 plus tan square y dy, and so dy by dx would be equals to 1 by 1 plus tan square y, but tan y is just x, so it is just 1 by 1 plus x square, right? So the derivative for tan inverse x, which is dy by dx, is 1 by 1 plus x square. Proving it, and all the other inverse functions can be proven in the same way, and corresponding to that we can find this integral. Evaluate integral of x to the power 4 by 1 plus x to the power 10 dx. Now at first glance, obviously we want to eliminate or substitute for the denominator, but we see that the derivative of 1 plus 1 x to the power 10 is not x to the power 4 dx, right? Or not any constant multiple of x to the power 4 dx rather. But what we can do here is denote the integral by I, by I, then what we get is this: capital I is equals to integral of x to the power 4 dx divided by, and we can write x to the power 10 as x to the power 5 whole squared, because in that case what happens is, if we substitute y equals to x to the power 5, what we get is dy is equals to 5 into x to the power 4 dx, right? And what we want is the value of x to the power 4 dx. So therefore x to the power 4 dx should be equal to d of y by 5. So our integral becomes I equals to integral of, this thing becomes dy by 5, and the denominator just becomes 1 plus y square. So taking the constant outside, we get 1 by 5 dy plus 1 by y square. Now since we already know the derivative integral for 1 by 1 plus y square is tan inverse y, but if we hadn't known that, what we could have done is we can use trigonometrical substitutions in problems where we have something of the form 1 plus x square or 1 plus y square in the denominator or in the numerator. Because if you substitute, and remember, obviously you can make as many substitutions as you can, there is no rule of making only a single substitution for a single integral. As you can see, I am going to make a second substitution now. I am going to substitute for the substituted variable itself. So substitute y equals to tan theta, where theta is another variable. Then dy would be equals to sec square theta d theta, if you remember the derivative of tan theta, and sec square theta is just 1 plus tan square theta d theta, and as you know 1 plus tan square theta is just 1 plus y square d theta. So therefore taking this on the left hand side, we get dy by 1 plus y square equals to d theta. So this whole thing becomes d theta, right? So therefore I equals to integral of d theta by 5, and integral of d theta by 5 is just theta by 5 plus c. But theta, as you know, if y is tan theta, then theta would be tan inverse y. Then the answer would be tan inverse y by 5 plus c. But we also need to put back the value of y, which we substituted as x to the power 5. So the answer would be tan inverse x to the power 5 whole divided by 5 plus c, which is our answer, right? Okay, so this is another problem, and let us do another one. This one would be from the section of IBP. So obviously whenever you're facing, or you're in a situation where you are in exam or some problem solving session, you might not be given the topic, right? So you might have to figure out on your own how to do a certain problem of integration. If it's a definite integral, or even if it's an indefinite integral, you might have to substitute for something. You might have to do integration by parts. So there are various ways to do an integral, and you need to figure out which way works for you, which way actually solves the integral, because other ways might actually make you go round and round and come back to the same integrand again, right? So let us evaluate x sin x dx, and after that we'll do a more complicated version of this. So denote by I the integral, and whenever we see functions which are product of two different kinds of functions, we try to remember our eyelet rule, where we obviously know which one to take first function and which one to take second function. So in the eyelet rule, as you can see, eyelet, the algebraic function comes first after the trigonometric function. So algebraic function should be part 1, function 1, and the trigonometric one should be function 2, right? Then we have I equals to x into integral of sin x dx minus derivative of x, which is d dx of x, into integral of sin x dx, and whole thing is dx here, right? Now integral of sin x is minus cos x, so this is minus x cos x dx, minus x cos x, minus d dx of x is just 1, and integral of sin x is again minus cos x, right? Then as you can see, it simplifies considerably into minus x cos x, and this minus make it a plus, and 1 into cos x is cos x dx, and you do know the integral for cos x dx, which is just sin x, right? So the answer is x minus x cos x plus sin x plus c. So this integral is something which just comes back around its own, because the trigonometric functions, the sin x and cos x functions, generally they come back around its own when you integrate them enough number of times. So for example, they have a period of 4 on integration, so if you integrate sin x 4 times, you will actually get the same result. So let us try to find out something else here. Next problem would be integral of e to the power x sin x dx. Now this is a problem where you would know why the denote by integral I is of paramount importance. Okay, let's see. Denote the integral by I. Then what we have is I is equal to e to the power x sin x dx. Now if you remember in the rule I late, e, that is for exponential functions, that came last, so obviously e to the power x is going to be the second function here, and sin x is going to be the first function. So applying IBP, or applying integration by parts, what we have is this: I is equals to sin x into integral of e to the power x dx minus d dx of sin x into integral of e to the power x dx dx, right? So what we do get is integral of e to the power x is just e to the power x, so it becomes e to the power x sin x minus differentiation of sin x is cos x, so cos x into e to the power x dx. Now this is another integral, so again we apply the same integration by parts technique with cos x as the first function and e to the power x as the second function. Notice how we have to do integration by parts twice here, and we are doing it, as you will see why. It becomes cos of x into integration of e to the power x dx minus the integration of d dx of cos x, and as you know, integration of e to the power x dx is just e to the power x. I'll just write e to the power x dx here. So it becomes e to the power x sin x minus e to the power x cos x, and d dx of cos x is minus sin x, and minus becomes plus. It becomes e to the power x sin x dx, and if you take it away from the bracket, what becomes is e to the power x sin x minus e to the power x cos x minus integral of e to the power x sin x dx. But notice that this is the integral that we started with, right? So this is denoted by I, which is a variable. So this becomes e to the power x sin x minus e to the power x cos x minus I, and on the left hand side we have I. So solving for I, what we get, solving for I, we get 2i equals to e to the power x sin x minus e to the power x cos x. Therefore I is equal to e to the power x whole into sin x minus cos x by 2, which obviously there is a plus c, which is the answer. So this is one of those integrals where you have to do integration by parts twice to get the answer. So this is a problem where we have basically the integral coming back on its own, and then we have to solve it like that. So this happens a lot of times.